In the last video, we found that for the random variable x, which follows the Poisson distribution with parameter lambda, we found the expected value is equal to lambda. In this video, let's derive the variance. So the variance of a random variable is just equal to the expected value of the random variable squared minus the expected value of the random variable and then squared. And so from the last video, we know that the expected value of x is just lambda. So in the end, all we have to do is to find a way to evaluate the expected value of x squared. And this term here will just become lambda squared. So now let's focus on this expression. To find the expected value of x squared, we can do this based on first principles. That's just the corresponding probability of each value multiplied by each possible value. So let's just use the symbol k to represent each value. So k squared times the probability of getting the value k. And then we know that for the Poisson distribution, the value k can range from 0 to infinity and takes on discrete values. So it can go from k equal to 0, 1, 2, 3, and so on. And so once we evaluate this, we will be able to find the expected value. So for the Poisson distribution, the probability that you will get the value k is just equal to e to the power of negative lambda times lambda to the power of k divided by k factorial. And so now let's do a bit of rearranging with this expression that we have over here. The first thing we can do is to note that when we start from k equal to 0, essentially this entire term has become 0 because we have a 0 multiplied by a non-zero term. So we might as well just start with k equal to 1 because k equal to 0, the entire term is just equal to 0. And then the next thing we can do is that we can do a bit of rearranging. So for the sake of making the terms look a bit better in our next step, let's just take away one of the lambdas from this term over here. And then for this k term over here, we can take one of them out and then cancel it out with one of the k's in the factorial, so it becomes k minus 1 factorial. Because in the denominator we had k factorial, so that's just k times k minus 1 times k minus 2. So if we can take one of the k's here in the numerator and then cancel it out with one of the k's in the denominator, so we're just left with k minus 1 factorial. And then another thing I'm going to do is to, instead of write this expression as k, let's just write this as k minus 1 plus 1. So it's still just k, but I'm doing this for a reason. And the next thing I'm going to do is to redefine this indexing term over here. So instead of using k equal to 1, let's just define k minus 1 as equal to n. So I'm defining this new term n that's equal to k minus 1. And I want to, instead of using k, I want to use n to express all the terms in this expression. So the thing we're going to get is, first of all, when k equal to 1, n is going to be equal to 0. So if we're changing the indexing term to an n, we're going to start with n equal to 0, and then it will range all the way from 0 to infinity. And then for k minus 1, this is just equal to n, so we have n plus 1. And then we have e to the power of negative lambda, and then now we have lambda to the power of n. So now you see why I took this lambda outside of the summation sign, because now the power sign here looks nice. And then instead of k minus 1 factorial, we have n factorial. And so you see that this entire term over here, this is just the probability mass function for the Poisson random variable. And then with a bit of rearranging, we can actually break this term up into two separate parts. So for the first part, we have this n multiplied by the probability mass function of the Poisson random variable. And then here we have a 1, so we just have a summation term for the probability mass function. And so if we take a look at these two separate summation terms, we actually know what they are equal to, because first of all, this term over here, we have n multiplied by the corresponding probability of getting n. So that's just the expected value of x, right? And in the last video, we found that this term is just equal to lambda. So if this entire term, this is just equal to lambda. And then for this term over here, we're just summing up all the probability mass functions. So if you sum up all the probabilities, you just get 1. So plus 1. Another way to think about this is to take a look at the Taylor expansion of e to the power of a lambda. If you sum up all these terms over here, what you're going to get is e to the power of lambda, and so that cancels out with e to the power of negative lambda, so you just get 1. So two different arguments, you get the same outcome. This term here is equal to 1. So now we know that the expected value of x squared is just equal to lambda squared plus lambda. So now we're ready to go back here. For this term here, we just have lambda squared plus lambda as we just derived, and then we have minus lambda squared, so obviously these two cancel out. So in the end, we see that the variance is just equal to lambda.